Moving now from the one platform, the NEA platform that we were working with, to this high density 26,000 electrode situation. What we can see is we've not only captured individual neurons firing accidentally down the dendrite, but we can also capture the rapid response just like we would on any other NEA. And we can follow this over data and culture, and you can see a heat map for all the 26,000 electrodes. We can capture the best ones that represent neurons. We can I know that some companies have done it. I've heard that it works okay. I think optimizing, I've spent a lot of time on the protocol for OLC system. That's one of the things. Differentiating stem cells in the neuron and monoculture makes them very, very big, also very delicate. 50% washes, you have to treat them, on the weekend. It's not always the easiest process to go through or to get the best data, but I know there are people that are doing work with that. And they've had the nanion, so that you can run that work.
Thank you, and be going calendly around the talk if you want to.
My name is Kapil Bharti. I'm a principal investigator at the National Eye Institute, National Institutes of Health. At NEI, I'm in a branch called Ophthalmic Genetics and Visual Functions branch. We focus on all kind of retinal degeneration neurodegeneration diseases that affect people of, from childhood to adult onset. So AMD focuses for the cell therapy project that we're working on and also for some of the disease modeling, but my lab and in our branch, we also work on many pediatric early onset genetic diseases that affect the eye. Stem cells, particularly iPS cells, are really in the center of fight for us. They can be used as a cell therapy, and the other, they can be used to develop new drugs. And we're using iPS cells for both these purposes to try and bring a treatment for AMD for patients affected with it. Specifically for cell therapy, what we're trying to do is to develop an autologous iPS-based retinal pigment epithelium patch for these people. So retinal pigment epithelium is a layer of cells in the back of our eyes that provides nutrients and functional support to the retina. So in AMD patients, this layer degenerates, dies off, and hence, because of that, the retina starts to die. So what we have done is we have created pigment epithelium as a patch from patient-specific iPS cells and have developed methods to deliver it back to the patient's eye. The cell therapy approach is to make iPS cells from patients, AMD patients, make the patch and bring it back to the back of the eye with the hope that it will continue supporting the eye, and patients' vision will be restored or at least won't deteriorate further. The process of making the patch takes about almost 6 months from the day we enroll the patient all the way to the final product. And so we have mapped out the whole process of making this patch, first making iPS cells from patient blood, banking them, and then from iPS cells going into making pigment epithelium, and then making a patch from that. The patch is basically pigment epithelium cells as a monolayer on a biodegradable scaffold. That's the 4 by 2 millimeter patch, which covers more than half of back of the patient's central portion of the retina. And that's how it's supposed to be delivered and hopefully provide protection in that central portion of the retina. The advantage of using that construct is that there are conditions where actually, because of RPE loss in the eye, the vascular network in the back of the eye dies off. So this tissue, this construct would actually replace both of them. And then it also provides an in vitro model how to study macular degeneration in a dish. So we're also using it for that purposes, where you can test new drugs or toxicity of drugs. So there are ways now we're kind of branching out from this existing technology to kind of bring the next generation of products. So my relationship with CDI Fujifilm started off almost 2 years ago when we contracted with them. The CDI Fujifilms have successfully delivered what they promised in that contract in terms of making that protocol robust enough, xeno-free, and compatible with GLP and GMP manufacturing. We're working very closely on HLA matched iPS cell lines on perhaps a second generation scaffold. I'm excited to work in the iPS cell field because I think this field has a lot of promise. For me, the most important thing this field brings is that we have the opportunity for the first time to work directly with patient material, human material, patient material in a dish, to be able to uncover all the genetics, how the patient genetics affect the disease in a dish, and to also bring patient-specific cell therapy products back. I think this possibility never existed before. It was really the discovery of iPS cells is what brought it in. I think this technology has huge potential, and I'm excited to be working on this technology.
Hello, welcome everybody. This is Victoria Echeverria. I'm a product manager here at CDI. We're just going to wait a couple more minutes to allow people to join in on the webinar, and then we'll get started.
both of these stages, and I'll show you all of these various aspects throughout my talk. So first things first, we want to show we want to really make our B cells from iPS cells, and we have optimized a very robust protocol to differentiate our B cells, mature our B cells from iPS cells. The process is about 10 weeks long, and it really requires a combination of different growth factors at different stages, which has been optimized based on previously published literature and a lot of work we have done in my lab over the past 5 to 6 years. And what we have also characterized is that the cells really go through these various developmental stages so that the epigenetic marks are correctly laid down as the cells differentiate into RB. They go through this neuroectoderm, RB progenitor, chromatic RB, all the way to mature RB stages. And in fact, we've recently published that we can really make functionally mature RB cells using our protocol. And at the bottom panel, you see we can also we make the cells that we make are pure. Here's an example of a dish full of pigmented RB cells, and we can prove by a flow analysis using several different RB markers we have done by now that we can easily get more than 98-99% pure RB cells. And something that is this protocol is so critical for us, for our lab, for most of the activities we do, we want to make sure that the protocol is reproducible, and that we have done by testing this over 30 different donors so far, for healthy donors, HLA matched iPS cell lines, clinical grade iPS cell lines, and several diseased iPS cell lines. So I'm not going to spend too much time on demonstrating that we can make functional RB cells. We have extensively published on it. As I said, just one recent paper and a previous paper in 2016, where we extensively characterize functioning of RB cells made from iPS cells, that these cells really behave like native RB cells with the protocols that we use for differentiation. They display, here's an example of electrical properties, their membrane resistance, transceptural potential, and how they respond to various physiological stimuli, pretty much like how native RB cells respond to. So that I want to start with the first part of my talk to show you a little bit about 2D disease models and drug screening application of iPS-derived RB cells. So in this case, in the first part of my talk, the focus is going to be try to model the dry form of macular degeneration. We want to create a situation where RB cells die off as it happens in AMD. So to do that, we really dived into literature and looked for what are the triggers for RB atrophy, what are the triggers for this disease. And it turns out that dry form of AMD is really initiated by metabolic insults and biological aging. And a number of reports published in the past 5-6 years have shown that if you treat in vitro RB cells in vitro with a complement-competent human serum, you can trigger some of the phenotypes of AMD and hallmarks of aging, and this is aging. Cells, and so we thought maybe we can try to replicate those findings with iPS cell-derived RB cells. And the idea would be that RB aging is triggered by this complement in the serum that causes inflammation in cells. So first we check whether the aged cells, which are treated with the serum, does it show reduced functionality. In fact, when we treat these cells with such a serum, we can see here, if you measure the transepithelial resistance of the cells, which is a measure of maturity, functional maturity of cells, formed by these tight junctions between neighboring cells leading to electrical tightness of the monolayer. You can see control cells from the monolayer give you resistance of about 700 ohms per square centimeter, whereas aged cells within 48 to 72 hours dramatically drop their resistance to 250 or 300 ohms per square centimeter, suggesting that cells are not functioning as well as they're aging with this stress. And one of the really hallmark of AMD is accumulation of ApoE positive deposits underneath RB cells called drusen deposits, which contain other oxidized proteins and lipids. And in fact, these cells treated with a stressor, which we call aged RB cells, have very severe accumulation of high accumulation of ApoE deposits on the basolateral or the underneath RB cells. And not just ApoE, we have looked for other markers for drusen. They're there. Fibrillin 3 is another protein for drusen deposit. We also see high accumulation of lipid deposits. So really, hallmarks of AMD, as seen in patients' eyes, can be replicated in these cells. Drusen deposits are really shown by also by EM. So when we look at these cells by EM, on the left panel you see control cells, nicely polarized apical processes, apically localized pigment granules. In fact, pigment migrating into apical processes, very typical of native RB cells, rarely seen in cultured RB cells, but we think because we mature our cells nicely, these cells also have pigment migration into apical processes. And when we age it, our RB cells, you can see apical processes are gone, cells look vacuoled, and underneath the cells, you can see deposits which are missing in control cells. And if I zoom up right here, you can see these really basal deposits that are reminiscent of drusen deposits seen in patients' eye. So with these, we're really confident that we have created a good model to study macular degeneration in these cells. And now we can start with patients' iPS cells and really try to correlate these phenotypes with patient genetics and uncover pathways that are linked to macular degeneration. Just to give you one example, we see that aging cells, as it's thought that aging is linked to inflammation, we see increased activation of NF-kappa B pathway as seen by cytoplasmic nuclear translocation of P65 component of NF-kappa B in these cells. So with that, really these cells allow us the opportunity to discover drugs that can undo some of these hallmarks of aging or AMD in these cells. So with these phenotypes, we performed a drug screen using a low-pack library which has about 1,200 pharmacologically active compounds, and looked for drugs that would protect cells from cell death caused by this stressor A23187, which causes proteotoxic stress, very similar to what happens in our cells. And the screen was performed for 48 hours. This red, blue, green, and yellow are 4 different 3-to-4 plates, in which had different compounds. Each well had a different compound. And this, after primary screen and a secondary follow-up, and in which we identified 40 drugs, we performed the dose-response curve, 7-point dose-response curve of all those 40 drugs, and identified these 3 drugs that had reproducible effect of protecting RB cells from cell death in response to this stressor A23187 within 48 hours. This effect was seen reproducibly across more than one iPS drug RB line, so that was the reason we picked these 3 drugs. And when we test these drugs on cells, sure enough, these drugs were able to undo activation of NF-kappa B, as shown by this example here. In aged cells, we see P65 in the nucleus, but when we treat these cells either with a blue, green, or red drug or yellow drug, we see P65 translocates from nucleus to the cytoplasm, showing you that inflammation is downregulated in these cells, and we have preliminary evidence that these drugs are also able to undo some of the hallmarks features of AMD in these cells. So with that, I will conclude the first part of my talk. I've shown you that we can generate functionally authentic iPS RB cells. With these cells, we can replicate some of the early hallmarks of dry AMD, and we've done it across 5 independent donor iPS cell lines. We can perform 3-to-4 drug screens using these cells very successfully, and with that drug screen, we discovered a few drugs that we think can suppress disease-associated hallmarks in vitro, and then can provide potential drugs for patients going forward. So now I want to move to the second part of my talk, switch from 2D to 3D disease models.